Okay, so I'm recording this for those who were gone. It does help a little bit that I can do this, and if students access it, then at least if they don't get the full picture, they get a lot of it. And so this is the answer for the first one. Any questions you have? Just a review, because I know you did this in class, 2 days off, then come back. All we're doing is finding the simplest ratio based upon the weights that we have and the percentages we have. So we take the mass, we find moles, we compare the moles. An easy way to compare the moles, so it's whole numbers, we take the smallest number of moles and divide it into everything. Then we get numbers 1 and bigger. And hopefully they come out to be whole numbers, or really, really, really close to whole numbers. If they do, then that's our formula. Okay? If they come out to really close whole numbers, then that's our formula. Okay? Don't make it any more complicated. Some of you like to make these way more complicated than they are. You just need to use a little common sense if you know ratios. So in this one, we divide them out and we get 1, 3, and 4. So our formula is Ag3PO4. They're really close to 3, 1, and 4. They don't come out perfect though. But they come out within a few hundreds, one way or the other. Higher or lower than the whole number. Okay? So those are the first two answers. CuBr2, AgPO4. I don't think anybody missed either one of those. Alright? So here's the kind of add-on that we have. The add-on is that, let's say that we take these percentages, we change them to grams, then we go through the process of finding the moles. So I'll do that real quick. I'll plug those in, and we'll get those real quick. I'm going to find my pen. Okay, so I will have students on the test. They will write an answer for this, and they will get most of it wrong. A lot of points will be taken off. They'll write it as FeO2. They will say that those numbers are close enough, and so they can round. Remember, they have to be within a few hundredths at best before you can round. So our first step here would be what?
Divide by the smaller one.
Yep, divide by the smaller, 1.25. So we get 1 mole of Fe, and then this one, when we do it, we get 1.5, I'll say 49 moles
That's a problem.
of oxygen. Well, it's not too big of a problem. Some of you think that's a huge issue. They should all come out whole numbers. What do I do now? I have no clue. Okay, now just think. Get back. What are you trying to do? You're trying to find the what? What are we trying to find?
Ratio.
Yeah, we're trying to find a formula. We're trying to find how many atoms of each one that you need in which to make this formula. Okay? With whole numbers. So keep in mind what the object is. So that's like 1 to 1.5, right? 1 to 1.5. We can't have a half of an atom. So think, common sense. This is the smallest ratio, 1 to 1.5. What do you think the formula will be? Yes?
Fe2O3.
Right, because that is the same ratio as the 1 to 1.5. It's just whole numbers, right? 1 to 1.5 is the same as what? 2 to 3. All right? So, now, some of you think this is like, oh, that's common sense. I can get that every time. But I will have students that will get to this step, and then they kind of freeze and not sure what's going on. But common sense tells you if it looks like it's 1 to 1.5, so that'd be the same as 2 to 3. So I'd multiply both of these by 2, and I get numbers really close to whole number, especially the second one. The first one is exact, so it's Fe2O3. Okay? All right, so let's have you take an opportunity to see if you can remember back from Friday doing these. I want you to go ahead and solve for the empirical formula for CAP and O that goes together. Remember, our goal is to get the ratio, whole number ratio. And if it doesn't come out to be perfect, okay, and we can multiply to get whole numbers, then that's what we'll do, to get a higher ratio with whole numbers involved. Okay? So go ahead, work through that. Got the next step. Guys, it's 1.5 to 1 to 4. So when you look at that, you go, all right, what can it be with higher numbers? Well, 1.5 to 1 to 4 is the same as 3 to 2 to 8. You don't even have to think I got to multiply by 2, because you know, all right, 1.5 to 1 to 4, when you take a look at that, would be the same as 3 to 2 to 8. Okay? So if it's 3 to 2 to 8, that would be multiplying everything by 2. It could come out this way, but I'd like it in this form. If you have it as CA3P208, that's fine. Now, I'm not going to count it wrong, but some of you that really get it will understand that P208 is off your polyatomic ion sheet, and there's a PO4 there, a phosphate. If I have 2 of them, then that looks like our charges balance out, -3 plus 2.
But you'll accept the other
Yeah,
one? Okay.
yeah. But like I said, if you really know what you're doing and kind of know how metals, nonmetals, and that work together and charges work together, this is the form you can see, okay, yeah, that's what it's going to be. Okay, because there's no such thing as a P208 polyatomic ion on your polyatomic ion sheet. There's no such thing as that. So, we're going to do some problems. I'm going to have you do some problems like that later. This next part, we're going to switch gears just a little bit. Okay? So, we're going to talk about this thing called the molecular formula versus empirical formula. A molecular formula would be like this on the board. I better do it on this sheet here. But a molecular formula... Oh, now I've really messed myself up. Okay. Molecular formula would be C6H12O6. That's what we call a molecular formula. The empirical formula is CH2O. Okay? For glucose. So when we plug in our percentages, this is what we'll generate. That's what we'll generate when we come up with our formula. But that's not the actual formula. Okay? This stuff you don't have to write down, but CH2O, if I would go through and calculate its molecular mass, or its formula mass, which would be taking all of its weights into account. So I got 1 carbon, which is 12.01. I've got 2 hydrogens, which is 2.02 total. Got 1 oxygen, which is 16. Add those all up. I get 30. If I look at this weight, and I'm not going to show you all the work, but it's 180 0.18 grams per mole. The empirical mass should fit in the molecular mass a whole number of times because it's the same ratio. It's the same ratio that we would get. It'd still be 1 to 2 to 1, but they're bigger numbers. How many times does 30 go into 180? 6 times. Okay? So that means this mass is 6 times bigger than this mass. It means it has 6 times the number of carbons, hydrogens, and oxygens. It's 6 times more carbons, hydrogen, and oxygen. So that means that weight's 6 times bigger, 6 times the carbon, 6 times the hydrogen, 6 times the oxygen. That's the actual formula. So let's transition that to what we have here. And I probably got the work shown for that from a previous class. So I'm going to switch to this one. With that, what I just showed you, how would you go through and figure out this formula? Tell me what I would need to do to figure out the actual formula, because when I add these two together, I get 13.03, okay, if I do it farther than just the nearest gram. Tell me what the actual formula would be and how you would get it. What would be the actual formula? These two numbers on my formula have to be the same, because the ratio has to be 1 to 1, but with bigger numbers included. So what do you think? Kevin? Right. All I have to do is divide 78 by 13.03. A formula, if you want that and need that, would be you take the molecular mass divided by the empirical mass.
And this is defined what?
The actual formula. Sometimes you don't get the actual molecular formula. So, what we would do, this is a multiplier that we would multiply all our subscripts by in our empirical formula. So in this one I get 6. So what would be my formula? C6H6. Okay? So anytime I've got an empirical formula, I want to compare it to the actual molecular mass. The way I do it is I take and find the empirical mass and then divide it into the molecular mass. And that becomes how much bigger my numbers are going to be at the end. So I would encourage you in this next one to do this one. It shouldn't take you too long to gain this concept, to get this figured out. I want you to do that one.
Okay, so wait, how do you get the molecular mass again? Is that what you do?
I'm giving you the molecular mass.
No, but I mean like this.
The empirical mass? The empirical mass is, I'm adding up just like I would a regular molar mass. I take the empirical formula and I add everything up so I can get what the empirical mass's formula weight's going to be. Okay? So, my empirical formula is NO2. My molecular mass is 92. Realize, okay, let's not lose, overall what we're doing. We're trying to find the formula. Okay, that's all we're doing. We know the empirical formula. We don't know the molecular formula. But we do know the molecular formula is either 2 times bigger ratio, 3 times, 4 times, 5 times. That's determined by taking the empirical mass and see how many times it's going to fit into your molecular mass. Yes?
Remove that not there.
You want me to just switch?
Thanks.
Darren is the greatest thing.
I added nitrogen, which is 14, and 2 oxygens, which is 32 total.
So this is okay. Which one's the real one? Not the empirical.
The real one is the molecular. This is the actual way in which that molecule goes together. This is how it goes together. So that's the way.
The longer way is the real one.
It is the actual ratio of the molecule. Yep. Sometimes you'll get the actual formula. Sometimes you won't get the actual formula. But I will give you information that you can just divide it out. Now, if these two numbers were the same, like this was 46 and this was 46, then my molecular formula is the same as my empirical formula. They're the same, BNO2. If they're not the same, then the number goes in there multiple times. And that multiple times would indicate, hey, I'm going to have to multiply all subscripts by how many times it fits into that, and then I can get my answer. All right, so here's the first part of your assignment is to find the empirical formula for these. So this is the same as what you did for today, but you have to take it one more step. It doesn't come out to be nice whole numbers. It'll come out to be numbers that you're going to have to re-evaluate and look at how can I increase each of these in which to get my mole ratio. Okay? If you would write those down real quick, then I can go to the second slide to get the other two questions you have to do. So these two and then two added on to that. Remember, when you come in the lab, we want to get started right away tomorrow. We do not want to take much time getting ready because this will take the full 50 minutes, or 49 or 48, whatever we have in class. And then you guys will probably have to put things away, which is you'll just put the Bunsen burner away, hot plate, and all, or not hot plate, but ring stand and all that kind of stuff.
Oh, that's
Oh, he was too busy with that.
I probably should put my videos to music or something.
That would be
Like what kind of music should I?
gospel.
gospel. Look up background music. Just Google back.
Really? You can have background music? Da 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 da.
There's some pretty good
Da,
background music.
da.
Yeah, sing us a song.